Hey everyone, and a huge, warm welcome to the channel. It's truly fantastic to have you joining us today. Before we dive into one of the most mind-bending and downright magical concepts in all of science, I want to take a quick moment to send you all the very best wishes. Wherever you are watching this, whatever you're doing, I genuinely hope you're feeling healthy, strong, and full of positive energy. May you and your loved ones be blessed with excellent health and happiness always. Okay, buckle up, because we're about to explore something that feels like science fiction, but is absolutely real: quantum entanglement. Imagine you have two special coins. Not ordinary coins, but magical ones, linked in a way that defies everything we know about how objects behave. You take one coin and travel to the other side of the world, say Australia. Your friend stays right here with the other coin. Now, the magic happens the moment you flip your coin. If it lands heads up, instantly, without any signal, without any time passing, your friend's coin in your hand will land tails up. Or maybe both land heads, depending on the rule. The point is, the outcome of one coin flip instantly determines the outcome of the other, no matter how far apart they are. They are perfectly coordinated, linked in a way that seems to ignore the vast distance separating them. This, in essence, is the incredibly strange and beautiful phenomenon of quantum entanglement. It's a deep connection between tiny particles, like electrons or photons of light, that persists even when they are separated by enormous distances as vast as across our planet or even across the galaxy. To understand how weird this is, think about how things normally work in our everyday world. If you want to communicate with someone far away, you need to send a signal. You call them on the phone. A signal travels through wires or the air. You send a text message. Data packets zoom across networks. You wave. Light reflecting off your hand travels to their eyes. All of these signals take time to travel. Light, the fastest thing in the universe, still takes over a second to reach the moon and over 8 minutes to reach the sun. Nothing travels instantly. But quantum entanglement seems to break this fundamental rule. When two particles become entangled, they share a single, unified quantum state. They stop being completely independent individuals and become linked parts of a single system. Measuring a property of one entangled particle, like its spin, a kind of intrinsic rotation, or its polarization, the direction its light wave vibrates, instantly tells you the corresponding property of its partner, no matter how far away it is. It's as if the information about the state jumps from one particle to the other faster than light, or perhaps that the distance between them becomes irrelevant for their connected properties. How do particles even become entangled? It often happens when they interact closely with each other or are born from the same source. For example, a single particle might decay into two particles. Or two particles might collide or interact in a specific way inside an atom or a specialized crystal in a lab. During this interaction, their quantum properties become intertwined and correlated in a very specific way that persists even after they fly apart. Think of it like taking two socks from a pair. If you only look at one sock later, you instantly know the color and pattern of the other sock, even if it's on the other side of the universe. But with particles, it's not just about knowing a predetermined fact like color. It's more like each sock was both black and white at the same time until you looked at one. The act of looking at one sock forces it to become definitively black or white, and simultaneously, instantly, forces the other sock to become the opposite. This is where it gets truly bizarre and different from our sock analogy. This instantaneous connection troubled even the greatest minds. Albert Einstein famously called it spooky action at a distance. He, along with colleagues Boris Podolsky and Nathan Rosen, pointed to entanglement in a famous paper, now called the EPR paradox, as evidence that quantum mechanics, as it was understood in the 1930s, must be incomplete. They thought there must be some hidden information, some local hidden variables, predetermined when the particles separated, that explained the correlation without needing faster-than-light spookiness. They believed the particles carried secret instructions about how they would behave when measured, set when they were together. For decades, this was a deep philosophical debate in physics. Was quantum mechanics truly this weird, or was there a more comfortable, classical explanation? The debate raged until the 1960s when physicist John Bell devised a brilliant theoretical test, now called Bell's theorem. Bell figured out a mathematical way to distinguish between Einstein's idea of hidden variables and the spooky, non-local connection predicted by standard quantum mechanics. He showed that if hidden variables existed, the correlations between entangled particles in certain types of experiments would have to fall within specific limits. Quantum mechanics, however, predicted correlations that exceeded those limits. The only way to settle it was to do the experiments. Starting in the 1970s and continuing with increasing precision ever since, scientists like Albert Einstein and many others have performed these tests. They carefully create entangled particles, send them flying off in different directions to detectors far apart, and measure their properties in specific, correlated ways chosen after the particles have separated and are too far apart to communicate by any known signal, even light-speed signals. Time and time again, the results have overwhelmingly violated Bell's limits for hidden variables and matched the predictions of quantum mechanics. The spooky action was real. There are no hidden instructions. The particles are genuinely connected in a way that transcends space. So, what does this mean? When scientists measure one entangled particle here on Earth, and its partner is, say, on a satellite orbiting the Moon, the outcome for the second particle is determined instantly by the measurement of the first, faster than any signal could travel the distance. It's not that information is sent faster than light in a way we can control or use for communication. We can't force a specific outcome on our particle here to send a message to the Moon. The results are always random. We only see the correlation after comparing the results from both locations. But the instantaneousness of the correlation is undeniable. The state of the two particles is fundamentally linked, and measuring one collapses the possibilities for both, regardless of the distance. This suggests that at the deepest quantum level, the universe isn't strictly local. Things that happen in one place can be intimately connected to things happening far away, without any physical signal mediating the connection in the space between them. Space itself might not be the absolute barrier we thought it was for these linked quantum states. This isn't just a weird laboratory trick. Quantum entanglement is the beating heart of emerging technologies that promise to revolutionize our world. One of the most exciting is quantum computing. Ordinary computers use bits that are either 0 or 1. Quantum computers use quantum bits or qubits. A qubit can be 0 or 1 or both at the same time, a state called superposition. But crucially, qubits can be entangled with each other. This entanglement allows quantum computers to perform certain calculations in parallel, exploring many possibilities simultaneously, solving problems that would take even the most powerful supercomputers millions of years, in a fraction of the time. Tasks like simulating complex molecules for drug discovery or breaking current encryption codes become possible. Entanglement is the resource that gives quantum computers their potentially immense power. Another revolutionary application is quantum cryptography, specifically quantum key distribution. Imagine two people, Alice and Bob, want to share a secret message so secure that no eavesdropper, Eve, can possibly intercept it without them knowing. They can use entangled particles. Alice and Bob each receive one particle from an entangled pair. They measure their particles randomly in different ways. Because the particles are entangled, their measurement results will be perfectly correlated in a specific pattern only if no one has tampered with them. If Eve tries to intercept and measure a particle to steal the key, her measurement collapses the entanglement. This disturbance creates errors and inconsistencies in the correlation pattern Alice and Bob see when they compare a subset of their results over a normal channel. They instantly know someone was listening and discard that key. It's a fundamentally secure way to share secrets, guaranteed by the laws of quantum physics. Entanglement acts as the ultimate security seal. Scientists are also pushing the boundaries of distance for entanglement. Experiments have successfully entangled particles across hundreds of kilometers using optical fibers, and even between the ground and satellites orbiting Earth. China's Michia satellite, launched specifically for quantum experiments, has demonstrated entanglement distribution over distances exceeding 1,200 kilometers. These experiments aren't just stunts, they are crucial steps towards building a future global quantum internet, where entanglement could link quantum computers and sensors securely over vast distances. The implications of entanglement go beyond technology. They challenge our very understanding of reality. What does it mean for two things to be separate if measuring one instantly influences the other across the cosmos? It suggests a profound interconnectedness at the fundamental level of the universe. The classical view of a universe made of distinct, independent objects bumping into each other breaks down in the quantum realm. Entanglement hints at a deeper, more holistic reality where things we perceive as separate are still linked in ways we are only beginning to fathom. It forces us to reconsider concepts like locality, causality, and the nature of space and time itself. While we can't use it to send messages faster than light or build Star Trek transporters, yet it reveals a layer of the universe far stranger and more wonderful than we could have imagined. So, the next time you look up at the stars, remember that the universe might be far more deeply connected than it appears. Tiny particles, born together or interacting briefly, can remain mysteriously linked, whispering to each other instantaneously across the vast emptiness of space. Quantum entanglement is a testament to the profound strangeness of the quantum world, a world that underpins everything we see and experience. It's a powerful reminder that science continues to uncover mysteries that challenge our intuition and expand our understanding of what's possible. From the potential of unhackable communication and unimaginably powerful computers to the deep philosophical questions about the fabric of reality, entanglement shows us that the universe is truly full of wonder. Thanks so much for exploring this incredible quantum connection with me today. Stay curious.